Hi, this is Mark Sarazano, registered piano technician from howtotunepianos.com and the International Piano Technician School. In this video, I just want to show you how I've gone through and identified errors in the Go APE system and how we use that knowledge to improve the Go APE sequence of tuning the temperament. So the first thing I did was I assumed that if a temperament sequence was accurate, then it would be able to produce a very high score on an ideal piano that has no inharmonicity. Now, some criticisms have been that, well, all pianos have inharmonicity. Yes, but what we're looking for is a temperament sequence that takes that into account. In other words, if it's a good temperament sequence, it will tune a good temperament on a piano with high inharmonicity. It will tune a good temperament on a piano with low inharmonicity, and it will tune a good temperament on a piano with no inharmonicity, which is what we're doing here. So that variation of being able to tune the best temperament depending on what inharmonicity the piano has includes this ideal situation where there's no inharmonicity. So that's the assumption that we're going to make, and it's a very good assumption because this assumption has resulted in me finding out some information that has improved the Go APE sequence that tunes real pianos. So that's where we're starting from. So the first thing we're going to do here is create this template where we have all the frequencies of equal temperament right here. These are all the frequencies of equal temperament. And then we're going to tune these frequencies here. So these are the frequencies we're going to be tuning, and they're going to produce certain criteria that we're going to compare. So when we make the comparison to the actual equal temperament, we're going to get an error. Now this error, we're going to calculate the average error to correct the error so that we don't get penalized. If all the notes are flat, but it's a great temperament, we shouldn't get penalized for that. So we remove the average so that we get the actual error from the average, and then calculate the loss based on that. So the first temperament sequence we're going to look at is this one, which is the common fourth and fifth temperament, where you make all fourths wide by 1 beat per second and all fifths narrow by 3 beats in 5 seconds, which is 0.67 beats per second narrow. So what I did was I simply went through here and changed these frequencies until the criteria was met. So this is the actual beats per second of each of these intervals that are produced. So for example, this fourth, I kept tweaking the frequencies until I got 1 beat per second wide. The fifth, tweak it until it was narrow by 3 beats in 5 seconds. And all of these worked out this way. Except when we got to the end here, the last fifth should fit, right? It should be about 0.67 beats narrow. This one was 0.25. That's not a big deal. It's not a big deal. All the octaves were tuned as pure 4/2s because with no inharmonicity, that is the best size. And so then these frequencies were compared to the actual correct equal tempered frequencies, which produced an error. And this error is mentioned here in cents. This is the error in hertz. This is the error in cents. And the total error, the average of all that error, was 0.71. So we just minus that. So all of these are sharp. So we minused it. So now the average of all this error is 0, because that's what we want to do. We want to calculate the error based off of how far away it is from an ideal, which is 0 cents. And this was the loss calculated on no loss for 0.25 cents off, but 2% loss for every 0.1 cent off after that. And so all of this loss added up to having a mark of 47%, which is not unusual to think because, as I've often said, the fourths and the fifths are not accurate when you make them 1 beat per second wide or 3 beats in 5 seconds narrow. They're just not, it's not accurate because the fifths and the fourths are increasing in speed throughout the temperament. So what about my sequence, the Go APE system? So the Go APE system is, again, with no inharmonicity, we can make a pure 4/2. I think here we've got the pure 4/2 and the pure 6/3. So what we're doing there is we're making we're checking 3 different beat rates, up to 3 when we have for example, we might have what's called the window, which would be the slow, medium, and fast. When we're tuning these octaves, we only need 2 beat speeds. So if they're the same speed, it's a pure 4/2. This is a pure 4/2. If these two are the same, it's a pure 6/3. So that's what we got here. We tuned the interval so it became a pure 6/3. Then we set the FA roughly 7, but it becomes corrected later on. And as we see here, it was corrected to the mathematically correct 6.9. So we tuned the skeleton, which is after the octave, the F octaves. Here's the F octaves, pure 4/2, pure 6/3. Then we tune the lower skeleton, tunes the correct C sharp, such that the beat rates of these 3 major thirds all increase in speed by the same amount. And in this case, 26%. So the first 2 are 26% apart, the second 2 are 26% apart. These are actually correct mathematical frequencies. And then the top skeleton, those 3 major thirds, again, same thing, mathematically correct, 26%. And that's after just tweaking these frequencies right here by hand, basically tuning by hand, adding a 0.1, minusing a 0.1, until this thing works out according to the criteria. And then here is where I just fixed the F4. If I happen to change the F4 from what it was here, I corrected it with the F3 and then ended up with the whole skeleton being 26%, all of them. That's what you see here. That's why it worked out. And it wasn't that way at first. It took a lot of iterations. Then now we start with the beat speeds. There's the slow, medium, fast, slow, medium, fast, slow, medium, fast. All of these, slow, medium, fast, slow, medium, fast, slow, medium, fast, slow, medium, fast. You can see here that the difference between the slow and the medium is the same as the medium and the fast, all through here. Correct. Equals. And so what that means is that it's agreeing with the criteria, which is that these three beats need to be the same difference. The ratios must be equal. And so, using all of these criteria, we have now tuned the Go APE sequence perfectly according to the criteria. So now the question is, what was the result? Well, here are the tuned frequencies. Here is the actual equal temperament frequencies, and here is the error. Error. What's going on here? That's what I thought when I first did that. Error in the Go APE sequence. This is not possible. And then we have the calculated cents out. We have the calculated average. We have the adjusted cents out, so the average is 0. Here we have the loss, and here's the mark, 75%. What? This was a shock to me when I first found this. And then I started looking at these numbers and trying to analyze. Well, this one's perfect, this one's perfect, this one's perfect, and this one's perfect. What is that? This is the skeleton. F, A, C sharp, F, and A. This is, or we don't use the A4, we're not measuring. But these are the skeletons. So why is there an error? Well, look here. The next error is all the same. 0.29 cents flat, flat, flat. What notes are these? F sharp, A sharp, and D. Well, where do they occur? Here. F sharp, A sharp, and D. Right here. Well, what happened here? Look at here. The FA, the GB surrogate, and the AC sharp. So the GB surrogate is causing a problem. It's tuning the D flat. And that's what I found out. Every time we use a surrogate, we introduce a little bit of error. So I'm going to show you where this error comes from. The major third, major sixth equality, which is what I've been saying all along, in which everybody talks about the major third, major sixth equality. But let's analyze what this really means. Here's a bunch of notes, and we know that A4 is 440 hertz. If you divide by 2, you get A3. Now the question is, what are all the frequencies between? Well, we use the ET ratio, equal temperament ratio, which is 2 to the power 1/12. And you can calculate all the frequencies such that when you get a complete octave done, the multiplication of all these ratios equals 2. And that's what you want. You want to multiply each of these frequencies by a number such that when you get through an octave, the result is exactly 2. And that's what 2 to the power 1/12 is. So here's all those frequencies from C sharp 3 to A4. And here are all the partials. Ideal partials, simply multiplying the frequency of the fundamental by the partial number. So here you got 220 times 2 is 440 times 3 is 660 times 4 is 880. And that's how we calculate the frequency of all the partials. And there you have all the partials of all the notes from C sharp 3 to A4. Now, you can take any of those and calculate any interval speed you want using the difference tone theory, which says that the difference between two frequencies is the frequency of the beat rate. So for example, if you have 440 hertz for A4 and another A4 that's at 441 hertz, you're going to hear wow, wow, wow. You'll hear a beat that's equal to the difference of those frequencies. 441 minus 440 is 1 beat per second. That's the difference tone theory, and it works. So how you do that is you simply take any major third, in this case, the major third built on F3, which will be F3A3, and you look at the coincident partial. In this case, the coincident partial is A5. So A5 is found at the fifth partial of F3 and the fourth partial of A3. The difference between those frequencies is the speed of the interval. The difference of the coincident partials is the speed of the interval. In this case, the difference works out to 6.9. That's why we say, have you ever wondered, why do we say F3A3 beats about 7 beats per second? This is why, because mathematically it comes out to about 7 beats per second. So there's your major third. You can do the same thing with all of the major thirds. So here's all the major thirds. And just as an aside, I found this interesting that the ratio between all these major thirds speeds is the same as the ratio between all of the frequencies of equal temperament. In this case, 5.95%, which is 2 to the power 112. Now you can do the same thing with major sixths. If you see here, we take this major sixth F3. The coincident partial of the major sixth F3D4 is found at A5. So there's A5 is the fifth partial of F3, and A5 is the third partial of D4. So the difference in those frequencies is the speed of the major 6. And we can do that for all the major 6 found between C sharp 3 and A4. And here are those speeds, again, increasing by 5.95%. So now the question is, where is the major third, major 6 equality? So if we look at F3, for example, you ask yourself, well, what major 6 is the same speed as GB? Well, the answer is none. There's no 7.8 here. But which one is the closest? Turns out that this one is the closest, 7.9. And the difference, like these are not the same, but we've been telling people that the major third, major 6, inside, outside, major third, major 6 equality is something that we use in equal temperament. But the fact is they're not the same speed, and the error for all of these major third, major 6 is the same, about 2%. Well, that's no big deal because we can't hear that difference anyways. We can only hear about 3 to 5%. That's our lowest that we can get. So anything lower than that is no problem. So the major third, major 6 equality in and of itself is not a problem if you just use it once. But if you look over here, we're using it here to tune D. So now, because the FD should be a little faster, the F3D4 should be a little faster. When we tune that D so that it's not a little faster, but it's the same speed as the GB, you're going to have a flat D4, again, by a small amount. And the same thing happens when you tune F sharp and A sharp. F sharp is just a little flat, A sharp is just a little flat. But then look what happens. After we tune the D, F sharp, and A sharp, now we're going to tune the D sharp. And it is tuned from the F sharp and the A sharp and the D. All three notes flat by the same amount. So when we tune the F sharp, D sharp, which is a major 6, assumed to be the same speed as the major third it replaces, we're introducing a second level of error. And now these notes, D sharp, G, and B, are all going to be a little bit more flat. And they are a little bit more flat. And then when we go to tune the E, we're tuning it from the GB and the BD sharp, which are all already now a little bit more flat, and this results in very flat E, C, and G sharp. And this is where it lost its marks, because the accumulated error created from all of the major third, major 6 assumptions, which are not a problem at the beginning, but can produce a problem where the E is audibly flat, producing a fifth that is too noisy, AE. Or this C produces a fourth, C4, F4, that's a little bit too noisy. Or this G sharp that produces a G sharp, C sharp, that's a little bit noisy. Now, when this happens, and it happened a lot to me before I realized this, I would notice, for example, that the G sharp, C sharp was a little bit too noisy, and I would use the Go APE system of looking for permission to fix either the G sharp or the C sharp, and there would be no permission. Why? Because all of the notes that are being tuned are equally flat, and therefore the beat rates are fitting in the slow, medium, fast. So the G sharp was tuned from the C, so we checked the C, no problem, it was fine. And then the C was tuned from the E, and it fit. The reason why it fit is because it fit inside the slow, medium, fast, evenly. But the criteria produced an accumulation of error. Therefore, if the E fits within the slow, medium, fast, it means it's flat. It means it's too low. So what that means and how we use it to fix this problem is this. The Go APE system always looks for permission. And in this case specifically, usually only this case is where I use it, the E4. If you want to raise the E4, which is if you do this sequence perfectly, you're going to end up with an E4 that's too low, and you're going to end up with a fifth A3 E4 that's going to be a little bit noisy. If you want permission to raise the E4, and you check it the way it was originally tuned, and it works out to be slow, medium, fast, then because of what I've just told you, you know that you have permission to raise the E4. Because if it fits in the criteria, it means that it's too low, because the criteria has this error in it, this problem of the accumulated error based on the using second and third generation of using the major third, major 6 equality. So just to wrap that up again, when you're looking for permission to raise the E4 and it fits in the way that it was originally tuned, that means you do have the permission to raise it, and you can raise it. So I hope that was helpful. This is an explanation of the major third major sixth equality and its limitations. This was a description of the Go APE system and how it works better by modifying your permissions just for the E4 to raise it if the E4 agrees with its criteria of the Go APE system. I hope that you enjoyed that. If you have any questions, reach out. I'm more than happy to explain this stuff, and I'll be as patient as I need to be to explain it to you. I love talking about this stuff, and I can talk about it all day long. Thanks for watching.